All right, so today we're going to look at vectors, but instead of the geometric vectors that we did yesterday, we're going to look at it more in an algebraic way. But really, more than anything, today is a lot about terminology and some notation, some basic vector operations. Now, the only introduction you probably have had to vectors would have come in geometry. And in geometry, we oftentimes, instead of calling them vectors, they were directed line segments. So you would have two points, P and Q in this example. P is your initial, Q is your terminal, meaning that is the direction that it is going. So we would call this a directed line segment. And it still had features about its magnitude, and magnitude tells you how long it is ultimately, and the notation for magnitude is these bars around it. So I don't have to say, hey, what is the magnitude? If you just see this notation, you know that I'm looking for magnitude. Now, for directed line segments to be equivalent, their features, their characteristics have to be equivalent, which means the two things, the direction and the magnitude, those must be equal. So if you look at this scenario, I have to show that the direction and the magnitude are equal. So looking at these two vectors, now I can look at it as a directed line segment, PQ, or I've gone ahead and named it vector W. And we're really going to use a lot more of the vector W, vector V, instead of the directed line segment. Okay, so let's think about this for a second. I'm going to go ahead and graph these two vectors on a coordinate plane, and I'm telling you your point coordinates. If I wanted to show you that the magnitude for these two vectors is the same, remember magnitude is the length, how would I show that these two are the same length? Why, yes, we would use the distance formula. All right, so distance formula could show that they have the same length or same magnitude. Now, you've done distance formulas since Algebra 1. I'm not going to take the time to do it. I know that you could do the distance formula on each of those to check to see if their magnitudes are the same. All right, the second characteristic is their direction. So looking at this scenario, how do you think we could show that they have the same direction? All right, hopefully you are thinking the slope formula. If you can show that they have the same slope, then that would mean they would be going in the same direction. Not taking the time to do that, and this is going to be a long enough lesson without having to do distance and slope, but know that that is how you would do it. Another way to look at showing that those vectors are equivalent is if you look at them in standard position. If they were both in standard position, they would end up lying right on top of each other. So standard position is when you put the initial point at 0, 0. So you can see at that previous slide, that would have been vector W. It was in standard position because it started at 0, 0. But the other vector did not, so it would not have been in standard position. But if you can think about all these vectors, if you were to put them into standard position where they started at 0, 0, then all you'd really have to pay attention to is their terminal point. And if you pay attention to the terminal point, you actually can write the vector in component form, indicating the coordinates of that terminal point. So when I see vector W being, this is component form, so the 3 is the horizontal component, the 2 is the vertical component. So ultimately I write 3 up to somewhere like right here, and we're talking about this vector right here. That's what that is indicating. In your notes, I do have a special slide to kind of show this. That component form is incredibly common. We will use it a lot. So be familiar with that term, component form. That means write it kind of like with the brackets, but they are pointy brackets. The first term is going to be your horizontal component, what's happening horizontally. The second one tells you what's happening vertically. Now, this is the diagram before I told you that vector W was in standard position, but this vector V is not. So if I wanted to figure out what this would be, if I slid it down into standard position, well, I'd like to be able to find what that terminal point would be without having to actually physically move that vector. So to find that, you're just going to take your terminal point and subtract your initial point. So I'm going to do it with the x's, and then I'm going to do it with the y's. If I'm looking at vector rs there, I would need to do, since I'm starting at r and going towards s, r is the initial, s is the terminal. So this would be point 1, this would be point 2. The order that you do this does matter. Not only like in all of our other formulas where you just have to be consistent with your x2 and x1, this actually matters. If I were to subtract these the other way, I'd end up with negative numbers, and then that vector would actually be pointing towards the third quadrant. So my direction would be wrong. So you must do x2 minus x1. So looking at that directed line segment RS, x2 is 4 minus x1 is 1. Now do it with the y's. It'll be a 4 minus a 2, and you get 3. Oops. I wrote a 4, but it didn't look like a 4. So 3, 2. Now what's handy here is that W, vector W, was already a 3, 2. And if I were to take this vector and move it down into standard position, it would lie right on top of it because they're equal vectors. And so the component form would be the same as it would be for vector W. Now, one of the characteristics that we've talked about with these vectors is the magnitude. Remember, direction and magnitude. We actually have a little formula that can help you find the magnitude. And really, it comes from the idea that if you put this vector in standard position, and then you sort of like create this nice little right triangle, you could actually do a little Pythagorean theorem on it. Because if I want to know how long this is, that actually would end up being like the hypotenuse. So I could take my horizontal component squared plus my vertical component squared should equal the magnitude squared. So right here, this is how I would find it then. To find the magnitude, notice the notation, the bars, all I'm going to do is that a squared plus b squared, and then I end up having to square root it, just doing Pythagorean theorem. All right, so in this problem, vector v, now this would have to be in component form for this to work and in standard position. So I would have the square root of this would be a 3 squared plus a 2 squared. Already doing the mental math there. That's going to be a 9 plus a 4. So I have a square root of 13. And that is the magnitude of, in fact, it'd be the magnitude in both vectors because they are equivalent vectors. So let's see if we could take some information and create this vector, putting it in component form. So two things here. We're going to find the component form, and then once it's in component form, we're going to find the magnitude of the vector. Okay, now I'm not giving it to you as a vector. I'm giving it to you as a directed line segment. So what it looks like is happening here is that my initial point is at 4, -7, so somewhere here. And then I have a terminal point at -1, 5 up here. And so my vector is going this way. So the first thing I want to do is get it put into standard position so that it would be written in component form. So for component form, I'm going to go ahead and just call this vector v. Remember how we do this. You take the terminal point minus the initial. So -1 minus 4, and then do the y values, 5 minus -7. So then if I simplify that up, I'm going to find that the magnitude, I'm sorry, not the magnitude, the vector in component form would be -5, 12. So if I were to shift this vector here and put it into standard position, it would come up here and then it would go out like this, and the terminal point would be -5, 12. So that's the first thing they wanted. The next thing they wanted was the magnitude. So the magnitude, let's go ahead and use our nice notation, magnitude is equal to square root. I'm going to ahead and showing the work, but I know you're going to get good at this and you won't necessarily want to show the work, and that's going to actually be okay. Did I really just say that? Okay, 25 plus 144, which ends up being the square root of 169. Wait a second. I think that's a perfect square. It is. So my magnitude actually ends up being 13. Right, so now that we know a little bit about some of the basics of vectors and some of the operations we can do or the notation and all that stuff, let's talk about what our goal ultimately is. Yesterday we were doing geometric vectors. We were drawing these vectors out, adding them or subtracting them, doing scalar multiplication, and combining them together. And it was kind of fun to do something different and draw out the vectors, but the reality is it's not the most efficient way to do that. And it's a little bit dependent on your precision as well. So what we're trying to do is we're trying to find an algebraic way to do what we did yesterday. So for instance, can we take vectors and just add them together? Well, that's what we were doing yesterday. We were adding them together. We were drawing them tip to tail. It looks something like this. So here we have vector V and I'm putting these in, that's in standard position. So 2, 5, there it is. Now I'm going to do tip to tail. So this one, if I'm going to do tip to tail, I can't put it in standard position. But where this one ended, this is now going to happen. So it's going to move horizontally left 7, and then it's going to move vertically up 2. So left 7, up 2. There it is. And then our resultant would be, what did we do from start to finish? So right here would have been my resultant. And so in component form, that resultant looks like it would be, looks like it went left 5 and up 7. Okay, so that would be that vector. Now, that was yesterday. That's what we did yesterday. Do you suppose that we could take these vectors and do that same idea, but do it algebraically so we didn't have to draw it out? For instance, if I'm trying to add these two together, can you figure where did we get these two numbers? Because ultimately I'm supposed to get the same answer here. So here's what we would do. We would be taking the 2, 5, and we would be adding the negative 7, 2. Well, think about it. It's not really all that difficult because this negative 5 is really just me adding the horizontal components together. And this 7 is just adding the vertical components together. So if I already have this, it would be super easy just to add the horizontal components, add the vertical components, and I've got my resultant. And I didn't have to draw that out at all. All right, so that's where we're headed, trying to do the geometric vectors, but trying to do them algebraically. One of the other things we did yesterday was that scalar multiplication. So you would take a vector times 2. So geometrically, what that looked like was, here was the vector, and then I doubled it up and made it go twice as far. So if I were to look at this graph, I know it goes off the graph, but do you suppose we could figure out what that would need to be? So this vector, this is vector V, so it went right 2 up 5, right 2 up 5. And then I did it again, right 2 up 5. So it looks like I'm going to end up at 4, and then it would be up 10 is where that would land. Okay, how do you suppose we could come up with a 410 without drawing it? Well, here's my scalar times the vector 2, 5, and all you're doing is scaling both of these numbers by 2. So a 2 times 2, there's your 4. 2 times 5, that's your 10. And you get 4, 10. And that is just easy peasy to do when it's in this format. So I'm not going to do the drawing today. I'm not going to keep showing that to you. Let's try one more. This one has a little bit more going on with it. So don't be afraid to take a few steps. Vector W. All right, that's negative 7, 2. And I'm going to subtract 3 times vector V, which looks like that. All right, and then I think I'm going to go ahead and distribute this -3 through there. Actually, you know what? I'm not going to distribute the negative. I'm going to leave the minus there and just distribute the 3. So then I'd have a 6 and a 15. So now, final answer to combine those through subtraction, I have a -7 minus 6, -13. Now I have a 2 minus a 15. That's also a -13. Okay, total coincidence, but that is my final answer there. All right, so let's take a look at unit vectors. A unit vector, and we will typically use a U to show that it's a unit vector, is a vector that has a magnitude equal to 1. That's all it is. You have this vector, and you want its magnitude to be 1. It's super short. So let's say I have vector V here. Could you find the magnitude of vector V? Well, sure, we could do that. Magnitude would be the square root of 9 plus 16. And what do you know? That's the square root of 25, which would just be 5. So the magnitude of my vector is currently 5. And I went ahead and I drew it down here. Left 3 up 4. There it is. It has a length of 5. But what I really want to do is I want to find the unit vector in the direction of vector V. So I can tell that vector V, the components of that would look like this, but it is not a unit vector. I want the unit vector, so it's going to be like going in that same direction, but way, way shorter. So I've got to work on finding that. Well, all you really got to do, if it was 5 and I want it to be a 1, just take your vector and divide it by whatever your magnitude is. So I could write -3/5 and 4/5. So thinking about what I just found in component form, I'd be left 3/5, up 4/5, and that would be the terminal point of that little baby tiny vector right there. All right, what do you think? I went ahead and gave us a slide in your notes so that you have, and this one doesn't have that border, but you might. It's pretty important. To find a unit vector, you're simply going to take, well, and I should say a unit vector in the same direction as some particular vector A in this case. I'm just going to take the vector itself in component form, and I'm going to divide it by its magnitude. If you divide it by its magnitude, that will bring it back down to the length you want it to be. So for instance, find the unit vector in the direction of vector V, and here's my vector V. So I want to find the unit vector. Well, let's see how long it is right now. It would be the square root of 4 plus 16. So that's the square root of 20, which I would want you to reduce. What does the square root of 20 reduce to? Yes, that is right, 2√5. So we just found what the magnitude of that vector is. Now what I really want is I want the magnitude to be 1 unit. I want it to be a unit vector. So what I'm going to do is I'm going to change vector V, and I am now going to call it vector U because I'm going to be changing the length on it, or the magnitude of it. So all you have to do, if the magnitude is currently 2√5, well, I'm just going to take the vector in component form and I'm going to divide it by that magnitude. Now we do want to reduce. I don't have to rationalize, but those 2's could sure break down. So I end up with a -1 over √5 and a 2 over √5. Okay, now just as a quick test, I'm going to find the magnitude of vector U. You don't have to write this in your notes, so I don't want to get it too cluttered. Just follow along here. What I would end up doing is I would be taking the square root of, I have a 1 over square root of 5. Actually, it happens to be negative, but I'm going to square it. Plus 2 over root 5 and square it. And then that would end up getting me a 1/5 plus 4/5. Oh, how nice is that? That would end up being 5/5, which is really just equal to 1. And the square root of 1 is 1. Okay, you know what? I knew that was going to happen. Did you know that was going to happen? We were finding the magnitude of a unit vector. Okay, so I went and manipulated vector v and turned it into this unit vector. Of course, it's going to have a magnitude of 1. That was the whole point of doing what we did. Now, one of the reasons that you want to have that unit vector is you can use it to find other vectors. So our goal here is to make a vector for a specific magnitude. So we just kind of made one up in class. I'll just make this up. We want to find a vector in the direction of, and I'm going to throw in some sort of a vector. I guess I'll call it vector v. And I'm just going to say -2, -5. Let's do that. And let's make the magnitude be, I don't know, 10. All right, let's see if we can do it. The given magnitude currently has a magnitude of, let's see what that would end up being. That magnitude would be the square root of 4 plus 25. Okay, so what I'm going to do now is I'm going to take my vector and convert it to a unit vector. Now that I know its length, the unit vector would look like this. -2 over the square root of 29 and -5 over the square root of 29. There's your unit vector. But what I really want is I want my vector to be 10 units long. So what I'm going to do is I'm going to take this vector that is currently 1 unit long, and I'm going to take it times 10 to make it be 10 units long. So when I take that first term times a 10 or a 10 over 1, oh, I didn't fill this in, then multiply by the desired magnitude. So I'm going to take that times 10. So right now I'm just going to write it so that I have it written in my notes. But then think of this as a 10 over 1 when you multiply it. And it's going to be -20 over root 29 and -50 over root 29. Now, I'm not going to do it, but ideally, if I were to run this through the magnitude formula that we have, it should end up equaling 10, because that's the magnitude we wanted it to be. Now, when we're dealing with vectors, we have something that we call the standard unit vectors. Unit vectors, these are the 2 simplest unit vectors we could create. So one of them is this one right here where you go 1, 0. So this is the unit vector, and we call it vector I. And then going up, over 0, up 1, okay, there's another unit vector because it's 1 unit long. Now, hang on to that thought for just a second, and I want you to follow along right here. Now, you might have an open box right here in your notes. You really don't have to jot this down. I'd rather you just watch. See? Eyeballs. Just watch. All right, so if I were to give you a vector vector V, and it's AB in component form. And all I'm doing is I'm going to kind of rearrange this. So ideally what would be equivalent to this is to write it as 2 separate vectors. I could write it A0 and then 0B. When I add these 2 together, I'm going to have an A, I'm going to have a B. Okay, so I've just separated it out. And I'm going to separate it even more. This A here, I'm going to factor it out of there so it looks like this. Now, again, whether or not you would have thought to do that, that's not the point. The point is that now this, if I were to take this constant and multiply it by the vector, I would get back to this. Same thing here with the B. If I were to multiply that times the vector, I'd be back up here. The reason I wanted to do that is I wanted you to notice this right here, this 1, 0 in component form. That's just vector I right there. And then for the B, there's your 0, 1. That's vector J. All right, so this right here is what we call the linear combination of the standard unit vectors. Okay, so linear combination, meaning you're going to be adding or subtracting here, of the standard unit vectors, I and J, right here. All that really means is that if I give it to you in component form, it's just another way to write it. The horizontal component goes in front of your I vector. The vertical component goes in front of your J vector. It's a plus sign. There's not a comma. There's not brackets. It's a plus. Unless B was negative, then it would be a minus. Okay, so this vector is written in component form. Pay attention to your directions. If they say component form, this is what they want. If they want it written as the linear combination of the standard unit vectors, what they want instead is for you to write it with a 3 vector I minus 6 vector J. This is the linear combination. Don't put it in parentheses or brackets. Don't put a comma. There it is. Done. Just a different way to write it. It means the same thing. Okay, so much new stuff today. I got one more kind of recap the whole shebang. Here we go. I want to find the unit vector in the direction of vector V, and I want it written in component form. So here's my vector V. I think that looks way too big to be 1 unit long. I'm looking for the vector that's 1 unit long, but I want it to go in that same direction. So all we do to find that is find the magnitudes. Let's see how long it is right now. So that would be the square root of 49 plus 9. So that's the square root of 58. That's somewhere between a 7 and 8 length there. I want to find the unit vector. So what I'm going to do is I'm going to take my existing vector, and now I'm going to call it vector U, and I'm just going to take those horizontal and vertical components and divide by the magnitude. So 7 over root 58. You do not have to rationalize that. And negative 3 over root 58. Now, if the square root of 58 reduced in some way, I would want to do that. I just don't have to rationalize the denominator. There's your unit vector. Now they want me to convert it to a vector written as the linear combination of the standard unit vectors. All right, all that means is changing it to a 7 over root 58 vector I minus 3 over root 58 vector J. Okay, let's see what the third part is. Find the vector in the direction of vector V such that its magnitude is 10. Oh, I just did one that was a 10. I should have chosen a different number. Okay, that doesn't matter. Really what you're doing is you're going to take 10 times the unit vector. And my unit vector that I found up here earlier happens to be in the direction of vector V. So this is it right here. I just need to take that times 10. And it doesn't really specify if they want it written as a linear combination of the standard unit vectors, or I think I'm just going to put it in component form. So I'm taking the unit vector up top times 7. And that would be 70 over the square root of 58, negative 30 over the square root of 58. And that vector is going the same direction as V, but it is exactly 10 units long. Okay. Make sure that you work on your homework tonight because we add to this tomorrow. All of this stuff has to come to you really quickly and naturally. It needs to make sense so that we can add to it tomorrow. So no procrastinating. Good luck.